Everyone, I am Megha Ramesh and I will be talking about the first assignment of design and analysis of reconfigurable systems. In this video, we will go through the step-by-step tutorial for building a one-bit full adder using Quartus Prime Design Suite software. The required tools are Quartus Prime Lite and Questa for simulation. And we also need to install the Cyclone 5 FPGA libraries for the FPGA board that we'll be using in the further assignments. Software, we open the Quartus Prime Lite. So in the Quartus Prime Lite, initially we design the schematic of a one-bit full ladder as shown here. So to design the schematic, you go click on File, then New, and a new schematic file will be selected here, and then you just double tap on the drawing board and you get to choose what symbol you want to place, and you can place a symbol there and connect them according to the circuit that is needed. So from this circuit, the Verilog code must be extracted. So to extract the Verilog code, you go click on File, Create or Update, and then create a HDL design from the current file. On creating this HDL design, we get a Verilog code for one-bit full adder. So this is the Verilog code generated by the software from the schematic that we've created. After that is done, set that as a top-level entity. After setting it as top-level entity, we have to extract the test bench from the Verilog file. So we click on processing, then start, and then we go click on start test bench template writer. After clicking on this, a test bench is generated and it is in the path of the Quartus 23.1 full adder, and it is stored in the folder. From the folder, that file has to be added here. After adding it here, it is then shown like this. But these edits have to be made later. So these test vectors are based on the truth table, and later it is compiled. So compilation is being done right now. It'll take some time. So compilation is checked for these many parameters: analysis and synthesis, place and round fitter, assembler, timing analysis, EDA netlist writer, and the design compiled. So as you can see, it's getting compiled here. And we can see in the report generated, it's getting updated by the number of pins that is used. And then slowly all the other parameters also will get updated as compilation proceeds. So as we wait for compilation, we'll have to look at the different parameters also that is needed to see what hardware components are used in the circuit that we've built. So we can see that as compilation is done, we can see 2 ALMs are used, and there are no block memory pets that is used, no DSP blocks used. The total pins, that is input output pins, are 5. And as compilation is completed for all the parameters that we wanted to be checked has been checked, and 0 errors, and there are 15 warnings, but there are no errors here. Then after this, you'll have to simulate this circuit. So go to Tools, click on Run Simulation Tool, and then RTL Simulation. So as soon as you click on that, Simulation cannot be done on quartus prime light. The quartus prime light is from Intel. Simulation is done on Questa. Questa is from Siemens. So you'll have to install a license, obtain the license, and then combine both of them so simulation can be done for the circuit that's being compiled. So Questa is opened here, as you can see. So we'll go check under work here. There's only the Verilog code here. We need to add the test bench for simulation. So we click on compile and we add the test bench file, and there are no errors, no warnings. And we go to the test bench, right click, then click on simulate, and all the parameters appears here. Then click on initial here, then click on add wave. So upon clicking on add wave, we can see the parameters are added here to show which one of them is needed for the test bench. Sorry, I had to remove that, but the necessary ones are kept here, and sum and carry out, that is the inputs and the outputs. So then you make it into nanoseconds, and here it's in hexadecimal, as you can see. Let's change it into binary. Then we run the simulation. Simulation is done for 100 nanoseconds, and then we zoom in on the graph. We can see some different waves appearing here. So this is the simulation wave for 1-bit adder. So we can test it for the first two numbers here. So when A is 0, B is 0, and C in is 0. The sum is also 0, C out is 0. When it is 0, 0, and C in is 1. Sum is 1, carry out is 0. We can see for here, A is 1, B is 1, C in is also 1. The sum is 1, carry out is also 1. So in the similar way, all the other inputs and the outputs are compared to the truth table, and it is verified that it is correct. So this waveform here is matching with the truth table's waveform. Then we go back to Quartus Prime. So in Quartus Prime, we go to Tools, Timing Analyzer, and then under Tasks, we click on Report Path. So with this report path, we can know what is the critical path of the circuit that we have done. So you add all the inputs here from, and all the outputs are added here. And then report path is clicked. And we see that the critical path is from Cn of input to S of output. So the time taken for it to go from Cn to S is 8.810 nanoseconds, which means this is the longest path in the circuit that's been given. So critical path is the longest path that is taken to obtain the output. Now we come to the second part of our assignment. In the second part of the assignment, we don't have to design the schematic. We directly write the RTL code here for Verilog and its test bench for a 1-bit full adder. So you go here to File, click New, then directly click on a new Verilog HTL file and OK. Then a new one comes, then type in your Verilog code, then do the same thing for the test bench, type in the test bench, And after both of it is done, click on compile. Since compilation takes a lot of time, I already click compile and all of it is compiled. And this is a compilation report. So we can see what hardware, how much of the hardware that's present is being used. And then we go to tools, run simulation tool and RTL simulation. And now we wait for Questa to open up. And it's open. Questa is here. And now we add files so that we can compile. We add test bench so we can compile. So we go to the folder where it's created. We go there. Add the code again, it's fine. And then add the test bench again. And now it's done. Go here, click on simulate, and all the parameters appear here. And click on add pave. We'll see which ones are here and which ones have to be added. So we need to add sum and carry out. Compile it. Run it. Then zoom it. And when you zoom in on them, you can see it is the same as the truth table. Same as the previous one, the waveforms are equal to the values in the truth table. You can also verify it here. So it could be done with the previous one as well. I'm showing it to you in this one. And then we go back to Quartus. We do a critical path. Then we go here. Then we click on report path from A, B, and C. Then C out and S. This time report path is shown here. We can see the delay of the schematic simulation is same as the delay for the RTL simulation. It's 8.810. But the critical path changes. It is from A to C out here. The critical path changes here because in the schematic we specify the design and we place the logic gates the way we want. But here in the Verilog code we just give the behavior of the design. So the entire circuit, the schematic is designed by the software itself. So it has the freedom to choose how to place its logic gates. So the critical path changes. And coming to the part 3 of the assignment, part 3 is of two parts. So we have to design a 4-bit adder in behavioral code as well as structural code. So here again we directly add a Verilog file and its test bench. So in the Verilog file we type in the Verilog code for a 4-bit adder and the test bench. Then we click on compile. After compilation, all of the parameters that is required is to be ticked, and then compilation report is seen. And we can see that there are more ALMs used here when compared to the 1-bit adder, and there are 14 total pins here. Then we go to tools, click on run simulation tool and RTL simulation. Then Questa opens up. I've already done this step here. So after Questa opens up, we go to library, add both of the files here and add the test bench as well. Then simulate this test bench. You get the parameters here, then add the parameters that has to be required in the graph and then run it here. So after running it, we get the output as shown here for the 4 bits. We can also see it here, like I mentioned before. So for each of the bits that's been mentioned here, the carry out and the sum is also seen. After verifying it properly, all of them seem to be correct. Then, to find the delay, we go back to quarters, click on tools, then timing analyzer. I finished this part already and we've already seen this twice. So when you click on this, a new tab will open, a new window will open, and we click on report path. Then we click on the inputs and outputs, and when the path is reported, we see that the delay is 7.726. The critical path is from A1 to C out. Second part of part 3 is structural code for a 4-bit adder. So when it's a structural code, it's different circuit designs which have to be placed manually next to each other so that the circuit works. So in structural code, we can't write a structural code directly for a 4-bit adder. So initially we start off with a 1-bit adder that's compiled, and then the parameters and the outputs from here is taken for a 4-bit adder, and then its test bench is written. Then both of them are compiled, all the parameters are checked, compilation report is seen, the number of ALMs used is seen, the total number of pins is seen, the DSP blocks used, the block memory bits used, and all the hardware components that's been used in the circuit is seen. Then after this, we go to tools and simulation tool and RTL simulation. So it directly opens into Questa. I've already opened it here. So after that, you just click on compile and click on the test bench and the other code, and then simulate it, and then add wave. Click on the inputs and the output parameters, and then after running it, this is the output waveform obtained. This is the same as the truth table, and this is correct. So you can see the outputs also here in the bottom. And then when we check the timing analyzer to see the critical path, I finished doing the critical path finder. So the delay is 7.916. Critical path is from P0 to C out. So when it was 1-bit adder and we compared the schematic simulation and the RTL simulation, the delay was same for both schematic as well as RTL. But the delay for structural coding for a 4-bit adder is more than the delay for behavioral coding, because in behavioral coding, the circuit is designed directly and it is compiled directly. Whereas in structural, it is designed in separate circuits, and the separate circuits are placed next to each other, connected, and then the outputs are obtained. So behavioral coding delay is lesser than structural coding. Thank you, and we'll be back with assignment 2 next week.